Well, good morning, everyone. It is a great pleasure to have you here today. My name is Jan Lauko. I'm the chair of the Queensland RACI Polymer Group Committee. Today we have Professor James Blinco from the Queensland University of Technology in Brisbane, who will be introducing Professor Jodie Lutkenhaus, a professor at the R.T. McFerrin Department of Chemical Engineering at Texas A&M University. And it's a great pleasure to have you both here. You both work on a very exciting area, and thank you for taking your time to be here.
Thanks, Jan. Yeah, it's my great pleasure to be able to introduce Professor Jodie Lutkenhaus. I'm doing this introduction as it was my suggestion to have Jodie here. She works in a very interesting and very active area of polymer chemistry, which is of interest to a lot of the groups that work here in Queensland, where they're working on redox-active materials. In particular, working on free radical and nitroxide type systems. So just as a little bit of an introduction, so Professor Lutkenhaus received her PS in chemical engineering in 2002 from the University of Texas at Austin, and then completed her PhD in chemical engineering in 2000 from the Massachusetts Institute of Technology. So she's now the William and Ruth Neely Faculty Fellow at the Department of Chemical Engineering at Texas A&M. So I guess she's sort of come full circle, starting in Texas and come back. It's sort of like being in Brisbane here. Most people start on the dark side at University of Queensland, but eventually they see the light and work their way over to Queensland University of Technology. I assume it's sort of something similar there as well. So she's got a long list of accolades that she's already been able to achieve, including the World Economic Forum Young Scientist, a Kavli Fellow, NSF Korea, and a 3M Non-Tenured Faculty Award, as well as being the current Deputy Editor of ACS Applied Polymer Materials. Her research interests are all around energy storage, so polyelectrolytes, redox-active polymers, and she's going to be telling us a lot more about that today. So thanks, Jodie, for taking the time in your evening to come speak to us about that today.
And also, before you start, Jodie, just a second, just a bit of a house rules. Please keep your questions till the end, and you can write them either in the chat or in the Q&A, or if you raise hand, I should be able to unmute you and you should be able to ask your question yourself. Thank you, Jodie. The floor is yours. Thank you, James.
Excellent. Thank you. Thank you, James, for thinking of me. I was just so excited to receive the invitation. I've never been to Australia before, and this just gets me one step closer, so thank you, and I hope to meet you all face-to-face someday. I would also like to encourage you, if any of you are get some questions or get some ideas after the fact with this presentation, I encourage you to contact me by email, and we can have a follow-up discussion. My email, you can find me very easily by Googling me. No one has my last name or has my name. And finally, as a bit of bookkeeping, if there's any connectivity issues, it may be hard for me to tell. So if someone, James or Jan, if one of you can come on and tell me if there's a connectivity issue or try to chat at me, let me know. Okay, so today we're going to discuss how redox-active macromolecular radicals can potentially contribute to our goal of achieving sustainable energy storage. And this is related to everyone's intense use of lithium-ion batteries. We use them in our phones, tablets, computers, and now there's immense growth in lithium-ion batteries for electric vehicles. And you can see this in this chart, where a lot of the future anticipated growth is projected to be in hybrid electric vehicles, and also stationary energy storage, like grid scale energy storage. So the demand for lithium-ion batteries is not going to go away. It keeps increasing. And in turn, we're going to start having to face issues with global materials supply. So here's something I want you to think about. This is a battery pack for a Tesla. And if you could look inside of it, it contains 7,000 little batteries. And each one of them looks like about the size of a AA battery cell. And that's just for one car. And that battery pack may be designed to last for 10 years, but how much raw material went into that battery? When its life is over, can we recover it? And if everyone decides to go to an electric vehicle, do we have enough materials to produce lithium-ion batteries at this scale in an economical fashion? So when we consider this question, we need to think about where do the materials come from and where do they go to? This is a materials supply and demand map from Joule, and it focuses upon several strategic elements that go into lithium-ion batteries, including lithium, cobalt, carbon, manganese, and nickel. Right now, you'll see a lot of news stories about cobalt because there are some social, political issues associated with it. Lithium is probably the next most sensitive or strategic element, followed by nickel, which is growing in demand. Most of these materials are going to China, which is symbolized, let me go to my laser pointer here, which is symbolized by these thick lines turning a shade from red, which is where the material comes from, to green, where it's going. So you can see most of the battery manufacturing is going on in China. And if you're from the United States, you might want to think about how can we manufacture batteries domestically in case we have some political tensions in the future. Just a practical thought considering where I'm sitting at right now. So it's interesting to think a lot of these materials actually don't come from the place that they're manufactured. And so our relationships with these countries become even more important. So the United States Department of Energy has identified strategically critical elements that we should consider. We can pay attention to how we recycle them or materials to replace them. And lithium and cobalt are considered on this list now. If you're working in the general area of batteries, you might think about working with materials that are more abundant, such as silicon anodes or lithium iron phosphate cathodes. Those are more abundant and their supply is more secure. So there are ongoing challenges for lithium-ion batteries. I just spent a bit of time talking about control of the materials supply. The materials are not necessarily produced where the batteries are manufactured, and materials map for the, or pie chart for the battery is shown on the right. Further, one of the problems right now with lithium-ion batteries is that people do not recycle them. They are recycled now in the United States at rates of 3 to 6%. And the reason for that is there is not an instated recycling program for lithium-ion batteries in the same manner that there is for lead acid batteries in your car now. So we need to think about how can we get people to recycle batteries, but further, how do we recycle batteries? And right now, how we recycle lithium-ion batteries is not fixed. There's not one process that has so far won out. Part of that is because the recycling of lithium-ion batteries is very energy intensive. Other issues, obvious ones, are safety, performance, and then the one that really drives me in this area is the social impact in developing countries. Half of the world's cobalt comes from the DRC, the Democratic Republic of Congo, and a large fraction of that is mined by children. So by moving away from cobalt, we solve not only issues with global supply and demand, but we can also benefit the lives of these children. Now, I'm a polymer scientist by training, so I'm always going to tell you that a polymer is going to save the day. So when I first began this project, I was thinking what types of polymers might be active in batteries, and to some extent, could we potentially make a battery that's as good as the ones we have now? In my group, we're also now considering the problem of recycling, although we haven't had papers on it. But for lithium-ion batteries, I told you recycling is very energy intensive. Taking the battery that we've just used, there are a few ways that you could recycle it. One is direct recycling, where you might simply take it apart and refresh the materials and reassemble it. But if you want to extract the strategic elements or materials from the electrodes themselves, then you have to do hydroprocess recycling, which is like a salt-based recycling, or you can you can do pyroprocess recycling. But again, there's not really a set way to recycle these batteries. So we've been thinking about the idea of organic-based batteries, as a lot of you have as well. And the concept is that the battery, which normally contains a cathode, an anode, and electrolyte, would contain organic materials instead. So instead of lithium cobalt oxide, you may have some redox-active organic molecule that can exchange electrons at either electrode. So to give you a general sense of organic versus lithium-ion batteries, I've provided these plots to you. And there are no numbers because we don't want to complicate things yet. But this is my general view of where organic batteries stand. Of the organic batteries that seem to have the most stable performance and the most classic chemistries, in my mind, I'm thinking about these nitroxide radical polymer-based batteries. They don't have the same equivalent energy as a lithium-ion battery. It can be close, and I think there's ways to increase it, but right now we're not there yet. So it's an exciting opportunity for research. In terms of power, the electron transfer is so rapid for these organic chemistries that we can achieve quite high powers. Because lithium-ion intercalation materials tend to be limited by lithium-ion diffusion, which is less of an issue for organics. For cycle life, for the materials I'm thinking of, they tend to not have the same level. They have good cycle life, but I think, in my opinion, it's not quite competitive with lithium-ion batteries yet. And we're going to talk about that quite a bit in the following presentation. The main reason so far is dissolution. A lot of these materials that look so promising will dissolve when you use them, and that leads to capacity fade, and that is unacceptable. In my group, we just put out a review article in ACS Macro Letters on macromolecular radicals. And so this is one graphic from that review. I encourage you to check it out. In my group, we have identified that macromolecular radicals are really exciting materials for this goal of sustainable, potentially recyclable batteries or energy storage. So I'd like to walk you through the length scale, arrow about how we think about these materials. So of course, with a polymer, I'll start with the backbone. We can have a variety of backbones. They're usually non-conjugated. You can have a conjugated backbone, but at the end of my presentation, I may convince you that's usually a bad idea. So we're usually looking at any type of non-conjugated backbone, and then attached to that is some radical species. So by mixing and matching the radical species in the backbone, you can have various theoretical capacities and voltages. So with that, if you want a really high capacity or also a high energy, you would want to increase the capacity, or if you want to have a really high capacity, you would want to have the lowest molar mass in the repeat unit. So this is a really different way of thinking from organic photovoltaics, where in organic photovoltaics, you're often adding these huge side chains to help with solubility, but we don't want that because that's going to damage our theoretical capacity. The next thing that we think about, and I think is not really well developed right now in the community, is how do these radicals pack and what is the chain conformation? And that's also something we're investigating now. Today, I'll be telling you more about how diffusion of the polymer is coupled to electron transfer for the macromolecular radicals. So all of these come together to affect how the electron transfers. And then I won't discuss it, but I would like to mention, I think we need to think more about the morphology of these, the solid state morphology of these polymers, and whether or not they really assemble into sort of domains or percolating pathways. So the long-term mission in my group is replacing metal oxides with renewable or recyclable polymers and enabling the use of earth-abundant elements such as silicon using conducting polymer binders. And then we also want to go to water-based processing. So that's my viewpoint. And today we will go mainly over the first 2 bullet points. If there's time, we'll visit the third. In the first bullet point, I will go over the concept of radical polymer batteries, the mechanisms of electron and ion transport, and then we will spend some time talking about solubility, which I think is very important, and I think it is under-discussed. And if time, we'll go over conjugated radical polymers. So first, we will go over the mechanisms of electron and ion transport in these types of polymers, and you can find more information from these papers. So let us first present kind of the workhorse polymer. This is called Ptma. So if you could have a representative polymer for the macromolecular radicals, I would point you to Ptma. It has a polymethyl backbone and then this tempo group hanging off. So when we synthesize this, this polymer is fortunately very tolerant of air and water. We can even store it on the shelf and use it later as we need. This is contrary to some other types of polymers, which you might have to watch very carefully in a glove box. So this polymer is used as a cathode in a lithium type battery, and we can store energy through the exchange of the electron and an anion. So this is very important because we're going to spend a lot of time on how this reaction actually proceeds. So we start with a neutral organic radical, and then we take an electron away, so we oxidize it, and we receive this oxoammonium cation. So because it's positively charged, we need an anion to come into the polymer and balance the charge, which we call doping, just as you would call it doping for a conjugated polymer. So the anion, which I haven't told you what it is yet, is we just call it X, balances the charge. So you have coupled electron and mass transfer occurring at the same time. And then we can reduce the polymer and retrieve the neutral organic radical. This potential, the potential of that reaction is 3.6 volts, just like it would be for lithium cobalt oxide. So the potential is really nice. The theoretical capacity is 111 milliamp hours per gram. So it's still, it's high, but it could, I would like it to be higher, maybe through some other chemistries. If we were to put this in a battery, it would have the same guts as a lithium-ion battery. Really, the electrolyte can be the same, the anode can be the same, it can be carbon. All we've done is switch out the cathode with our Ptma, so you can see it going between the radical and the cationic states. Different from the lithium-ion battery, in the cathode, we're exchanging these anions. In the lithium-ion battery, you would still be exchanging the lithium cation, so that's something different to think about. Before I get into the next part, I want to note this is kind of where, when I entered into this field, this is kind of where people are working mostly, to my knowledge, with these radical polymers. So you'll notice it's not metal free. There's still lithium there, and the electrolyte is still non-aqueous. And there's a lot of people working on different parts of that problem. So when I came in here, I thought these are really strange molecules. How do electrons transport? Because it's not conjugated. The charge is, the electronic charge is going to be very localized, not delocalized over a backbone like a conjugated polymer. And then how do ions transport? Because my background is actually polyelectrolytes, and so and solid polymer electrolytes. So do ions transport like PEO, or do they transport as they would in a polymerized ionic liquid? So those are ideas that motivated me. In this slide, I wanted to just show you that there's a variety of ways to make Ptma. This is that workhorse polymer. You can do free radical polymerization and raft, and among other means. It's hard to get high molecular weights, which I think is an important area to go after. I don't think that's discussed much in the literature, but it's something we've noticed. And at the same time, if you want low dispersity, then you're often limited in molecular weight. So as we've gone forward trying to do studies on molecular weight tendencies, these are things that we've come across. So in our group, we tend to do raft. We've found that gives you a good combination of control over molecular weight and dispersity. So several years ago, this really bright student from Hiro Nishide's group and Kenichio Yasu's group at Waseda University, he spent a few months in my group. His name is Kan Sato, and he's back at Waseda now. He had synthesized a whole suite of non-conjugated redox-active polymers, and he brought them to my lab for characterization. And out came this really beautiful paper in JAX, where he was able to determine that the mechanism of electron transport in organic radical polymers. So basically the electrons are hopping from radical to radical. That was already assumed and not new news. But the new feature that he added was that physical diffusion of the polymer chain is a really major part of how the electrons can hop from group to group. So before this, models had been assuming that the radical groups were kind of frozen in place, but really we need to remember polymers have some segmental mobility, and so these spheres, if you can imagine, can knock against each other once in a while as the polymer is wiggling around, and that's going to contribute to how the electron transfers. So we consider two methods of transfer. One is electrons exchanging from group to group. We can talk about inter versus intramolecular charge transfer. I'm not sure that that's really clearly defined right now. I've seen people claiming either one, and I'm not sure which one really dominates, honestly. Then once the electron gets close to the current collector, it can hop into the current collector to then transfer charge to the external circuit, and those are represented by the heterogeneous rate constant and the apparent self-exchange constant. And then now we need to consider the physical diffusion constant of the polymer, which Kahn got it through light scattering, but there are certainly other ways to do it. This is a whole series of polymers that he brought over from Waseda University. So you can see the top row consists of a lot of nitroxide radicals, and the bottom row also contains redox-active groups on these non-conjugated chains. So experimentally, he was looking at these different polymers. Okay, now let's dig in a little bit to the theory. So let us look at this heterogeneous rate constant. So that's the action of the radical jumping from the polymer to the current collector. So the heterogeneous rate constant now can be considered with the diffusion coefficient of the polymer. So that allows you to consider, if you hear children, they're mine, so sorry. So that's also dependent on the electron transmission coefficient, the mean free distance, so that hopping distance, and a reorganization energy. And the other rate constant we consider is the self-exchange rate constant. So that's from site to site. So besides considering like Marcus theory, we also consider the diffusion, the contribution from diffusion of the polymer chain. So together, that allowed Kahn to develop this model, which is the blue dashed line, for the self-exchange and the heterogeneous rate constants, and experimentally measure those constants in our lab for that series of polymers I showed you. So the agreement is not perfect, but it's also not terrible either. And I think the agreement is much better than previous models. So this is indicating a design parameter for all of us, which is if we want to facilitate electron transfer, which would ultimately result in higher power for your battery. We need to make the polymer as diffusive as possible. However, the problem is when you get a polymer that tends to have high segmental mobility, you're also looking at a dissolution issue. The polymer, usually the way you get a polymer to be mobile is also a way you get it to be soluble. So we'll touch upon that in a moment. The next thing we consider is how ions transport. So we talked about how electrons transport. How do the ions transport? And I would like to remind you that we're moving some, if you hear children fighting, I assure you they're mine and no one's dead. So sorry, hope you can't hear them. All right, so anyway, we have this anion transporting from the electrolyte into the electrode and vice versa as we reduce and oxidize. So if our electrolyte is lithium triflate, then the anion we're transporting becomes this triflate anion. And you can actually calculate for every coulomb of charge that I pass, what would be the change in mass of the electrode due to the anion transport. So this theoretical value is 1.54 milligrams per coulomb, and we're going to be comparing against that. Okay, so the way we would like to understand mass transport in situ is by using electrochemical quartz crystal microbalance with dissipation monitoring. So in our lab, we've developed a cell that can do this in a non-aqueous environment. And I would like to say it's not trivial. It's not the easiest measurement, but once it's well developed, it's very rewarding. I trust that many of you are not familiar with QCMD, so I'll briefly go over its working principle. The QCMD uses a piezoelectric quartz crystal to measure changes in frequency and dissipation, which ultimately correspond to changes in mass, absorbed mass, or even the mechanical properties. So I would like you to imagine if you have an old time watch, not a smartwatch, but an old time watch, that battery in your watch, apply some voltage to this quartz crystal. It will cause it to resonate at some particular frequency, which helps the watch keep time. So there's this fundamental frequency associated with the quartz crystal. If we add some material to that crystal, the frequency of the oscillation will slow down because of the mass. And if we measure the change in frequency, then we can use some viscoelastic modeling to actually estimate what that mass was. And then with dissipation monitoring, we can monitor how the signal decays or dissipates, and we can get a sense of if the polymer electrode is rigid, soft, and in some cases we could even model the shear modulus with viscoelastic modeling. So the raw data will consist of changes in frequency and dissipation. We can do viscoelastic modeling. If your film's really rigid, we can use Sauerbrei model. That is almost never appropriate for a polymer electrode. Most often you end up having to use a Voigt model or even a modified Voigt model to account for the viscous component because of that viscous response. Okay, so for the setup, we have a 3 electrode cell, but it's all encompassed around this QCMD crystal. So the working electrode is our Ptma coated gold quartz, Ptma coated gold coated QCMD sensor. And the counter electrode is platinum plate. We have a quasi-reference electrode, which is silver wire. We can then later calibrate it with ferrocene to know the potential, to estimate the potential that we observed. The electrolyte is 0.5 molar lithium triflate and propylene carbonate. And then again, this is the theoretical delta M over Q we're expecting. And then we just go do cyclic voltammetry for this experiment. You could certainly do other experiments such as galvanostatic charge discharge. This is an example of the raw data that you would get from the eQCMD module. So in the bottom, we have voltage. So this is the input is voltage. So I'm telling the instrument to scan voltage, and the output is current. So conventionally, this is just a cyclical tamagram that I've unpacked in the time domain. And we're doing different scan rates of 10, 25, 50, and 100 millivolts per second. The added feature of eQCMD is that we're getting the raw data in real time, consisting of changes in frequency and dissipation. And all I want to note for this graph is that these step changes in frequency and dissipation are coinciding with peaks in the current. So you already know that something is happening with the mass, and also here the mechanical properties when we go through a redox reaction. This is the same data, but we've repackaged it. Instead of plotting in the time domain, we're now plotting it as a function of voltage. So these are the CVs that you're probably more used to seeing. And then side by side, this is the change in frequency that was measured simultaneously for the different scan rates. And I just want to note that there's some interesting features. You can see these little bumps, or it looks like there's a few peaks kind of overlaying each other. We've seen this before and other people have in the past, but at the time we were kind of ignoring it, thinking, oh, that's some unexplainable feature, but they kept appearing. And as we went through the analysis, as you'll see, there's actually a real physical meaning for those peaks. There's still the reduction and oxidation of the nitroxide radical, but those peaks manifest from different modes of ion transport in the polymer, whether a lithium is participating or whether an anion is participating. Okay, and then the general behavior we see on the right, as we oxidize, as we oxidize the polymer, the frequency decreases, which we have to think kind of inversely. That means the mass is increasing, and that's correlated with the uptake of a triflate ion overall. So that makes sense to us. And then we can do the viscoelastic modeling to calculate the mass. Okay, so now we want to calculate delta M over Q. I'd like to tell you about how we do this. So we did the Voigt model for a half cycle of a CV. So you could do this for an oxidation cycle or a reduction cycle. We plot mass, and we're just going to take the change in mass from these two different plateaus and just call that delta M. And then for Q, we take that as the integral under the peak in the cyclical tamagram. And we do that for each scan rate. So on the left is delta M versus scan rate to the -1/2. And on the right is Q versus scan rate to the -1/2. Q is linear with negative square root of scan rate. That indicates to us that the reaction is diffusion limited by the electron, not necessarily diffusion limited by the ions. And this finding was not surprising, considering that Ptma is not really known for its electronic conductivity. Okay, so we're taking the plot on the left and the plot on the right, and we're dividing delta M over Q, and now we're plotting it by scan rate to the 1/2 because Q is now in the denominator. So our results are linear. Delta M over Q is linear with scan rate. We've also seen this general to other electrolytes. I mean, like other salts. And then here, what we kind of wrestled with for a few months was that the delta M over Q value is always less than the theoretical value. And then it was just really hard to get around that. But after some thinking, we were able to consider, well, maybe the mode of mass transport or ion transport isn't as simplistic as I thought it was. So what I was introducing to you was this idea originally that there's some electrolyte out here, and when one of these sites becomes oxidized, an anion comes and diffuses in and dopes the polymer, and we're all happy. But the picture is now revealed to be much more complex than that. The polymer is actually swollen with solvent and electrolyte. So the real case is the polymer already has some salt in it naturally. And so when we have a doping, event, two things could happen. One is the anion, which is already there because it's swollen with electrolyte, is in the close vicinity and immediately dopes the oxoammonium cation. And that leaves this lithium cation kind of unmarried. It doesn't have a place to go, so it will diffuse out to maintain electroneutrality out into the electrolyte. So if that occurs, then the delta M/Q value would be based solely on the transport of a lithium cation leaving the electrode. So it would be negative and it would be a small value. And then in the other case, we may have, if the lithium cation doesn't diffuse out, this anion can still come in from the external electrolyte to marry or pair up there. So there's a few different situations that can be going on, and I haven't even begun to talk about the idea of solvent transport. So, anyway, to get a better idea of this mechanism, I asked my student to go to an extremely low concentration where we can consider the electrolyte to be solvent separated, so there's less chance of contact ion pairs or ion clusters transporting in, so it simplifies the picture. And through that, we're actually able to see features of both of these ion transport mechanisms. So this is the CV for the low concentration case. And then we plotted delta M versus Q, and which is a running integral of the oxidation plot. And we can actually see that when we go through the lower potential peak, the mass actually decreases. And that's affiliated with the lithium cation getting kicked out of the electrolyte, or of the electrode, as we described in the first case. And then anion uptake takes over, which is the original case we were assuming. So now that we've observed that, we can assign mechanisms to those two peaks. The other interesting thing is when we go to those really low concentrations, the electrolyte is solvent separated. So now we have a lot more participation of the solvent, so we cannot ignore the solvent anymore. Our theoretical mass delta M/Q value is our observed delta M/Q value is much higher than theoretical. So if you do a mass balance on it, you can estimate the number of solvent molecules that come in. So you may say at this particular scan rate, for every one triflate anion I bring in half a propylene carbonate molecule. Or really, that is really to say that for every 2 triflate anions I bring in 1 propylene carbonate. Obviously, there's a lot of assumptions that go into this calculation. I want to shift over into talking to one of the problems, which is dissolution. I think all of you are probably facing dissolution with your redox-active polymers if you're working on it in the solid state. And if you look at our data, you see there's the drift in frequency, and the drift is too large to be assigned to an instrumental artifact. It actually has to do with dissolution of the low molecular weight fraction of the Ptma. So we have a 14% mass loss that just is not recoverable. But then after that, the higher molecular weight fraction remains. So that's something we need to think about. So one way to address dissolution is through cross-linking and then solvent selection. So I'm highlighting these few papers here that we published that go over that. So for cross-linking, we want to cross-link the polymer, but not too much because we want the electrolyte to still get in there. And so swelling is okay, but not dissolution. And most of these materials in a practical battery have carbon additives to enhance the conductivity. So our cross-linking scheme preferably is compatible with carbon. Most approaches are not, actually. And then we want minimal effects on radical content. Cross-linking before has been done in the melt, but we don't want to mess with that. We want to use standard battery processing techniques like solvent slurry casting. So there's that. And then we want the electrodes to be thick. So we want it to be practical. So photopolymerization really isn't going to work for these requirements. In this case, we're still making PTMA, but we're adding a little bit of glycidyl methacrylate as a cross-linker, and we looked at very low concentrations of 1, 3, 5 mole percent of GMA, or glycidyl methacrylate. We compared photo cross-linking and thermal curing for these different compositions. And the main message I want to get to you on this slide is that photo cross-linking is a bad idea. There's something about the light that is either damaging the tempo radical or causing some side reaction where the photo cross-linking is causing you to lose a great deal of radical activity. However, if we thermally cure above the glass transition of the polymer, then we can still maintain a lot of the radical content that we were looking for. We lose some, but it's much better than photo cross-linking. And you can see that in this EPR, in these EPR curves, where with photo cross-linking, you pretty much lose the signal, and with thermal cross-linking, the signal diminishes, but it still persists. This is EQCMD of the cross-linked PTMA, and with all of these compositions, whether it's 1, 3, or 5 weight percent glycidyl methacrylate, we have very little mass loss. In some cases, we even have mass gain as we're cycling it, because electrolyte is penetrating into the electrode in a process we call conditioning. So, you know, depending on what you're looking for, any of those compositions might be okay. I think 1 weight percent, we have a little dissolution, but it's really not too bad. Now you can see the dramatic effect of cross-linking when you build a battery with it and cycle it. In all cases, the cross-linked cell performed much better than the uncross-linked cell. This is because we've addressed these issues with the materials dissolution. We do have varied behavior, but I think we describe it more in the paper, but I think it's related to some interplay of swelling, because the 1 weight percent swells a lot, the 5 weight percent doesn't, and the radical concentration, because there is variation as we change the composition. So I'm not going to go into that. Okay, so besides cross-linking, polymer solvent and polymer additive interactions are really important. And I thought, oh, we can solve this problem by just selecting the right solvent. But when you get into it, there really isn't any knowledge of Flory-Huggins interaction parameters, to my knowledge, for PTMA. And so, so that presented the problem that we needed to identify solubility parameters so that we can now begin to estimate whether or not these polymers were going to dissolve. So sometimes you want the polymer to dissolve, like in the case where you're trying to cast it to produce the electrode. And in another case, you don't want it to dissolve, as in battery operation. So if you try to do group contribution, you'll see, at least to my knowledge, there's not a group contribution for the nitroxide radical, the oxoammonium cation. So we've tried to estimate it here with these other groups. But really what we need to get at is we need to understand the full structure of the polymer, and then we'll do some solubility spectrum so that we can then give you solubility, we can give the community solubility parameters so that everybody can benefit and control whether or not their polymer dissolves. Now, one of the things I want to emphasize to this community is that when we make a radical polymer, it doesn't always look like the chem draw that you want it to be. You actually have some fraction of the oxoammonium cation and this amine group present in your polymer. And if you really want to understand your material, you need to characterize it and quantify how much of this X, Y, and Z you have. And depending on the oxidation method, you will have different ratios of these 3 groups. And so that's something we characterized and using XPS, and I would encourage you to do that as well. So for solubility studies, we need to know this because we're trying to eventually report solubility parameters for these groups. This is just a picture of the solubility spectrum we produced. When PTMA is oxidized, that's the PTMA plus, we purposefully oxidized it to represent the oxidized state in the battery. Interestingly, it is insoluble in almost everything. PTMPM, which is the precursor to PTMA, is soluble, very easy to work with. PTMA is soluble in many things, but not everything. These are the solubility sphere projections. I don't have much to say about them for the time limit of this talk, except that I want to emphasize to you that the polar and the hydrogen bonding contributions for these Hansen solubility parameters were most predictive of solubility. So Hansen was more descriptive than Hildebrand, so I would encourage you to use those instead. And from a combination of turbidity titrations that we did and the solubility spectrum, we were then able to tabulate those solubility parameters and then produce estimates for the group contributions, which are now in the paper published online. Further, because that, we could then predict the solubility parameters for some other common radical polymers such as PTO and PTB. Okay, and then moving along for that, because we now know the solubility parameters and the behavior of the polymer, we can then predict what should the electrode composition be and what should the casting solvent be. And we did that by looking at the solubility sphere projections for a variety of binders, the polymer and carbon additives, and then potential casting solvents. And we settled on this composition. And what we saw was that if we used the predicted composition, we have really good electrode stability. In fact, the CV is even growing in as electrolyte begins to penetrate it. So it's not dissolving, it's actually compatibilizing with the electrode. And if we use the conventional electrode formulation, the electrode eventually delaminates and we have a loss of activity, which was the original problem. So you can see that here where our predicted composition has a capacity retention or a capacity that's generally 2 times higher than the conventional composition. That's with the same electrolyte. We just optimized the casting procedure. I don't want to take up so much more time because if you're like me, you don't want seminars to go too long. So what I want to do is just kind of briefly summarize some main points from our work on conjugated radical polymers. And if you're interested in it, you can ask me during the question session. We could go a little deeper. Radical polymers really are not very conductive. So there's been a lot of work on adding a conjugated backbone to possibly enhance the conductivity or even the electrochemical activity. But to date, most of that work has resulted in terrible conductivities and electrochemical activity. And we wanted to understand why. So we have a series of papers where we worked with P3HT that's been linked up to a tempo group. And we've examined and shown that indeed the actual capacity of these polymers and their conductivity for a series of carbon spacers is really terrible. And we have now shown why. The reason is that the tempo radical has one given redox potential of 3.6. The polythiophene backbone in our hands has some redox potential of 3.8. And so because they have mismatched potentials, when you start to reduce and oxidize the electrode as a whole, you have internal electron transfer between the 2 species. So it's analogous to almost like fluorescence quenching. So you have quenching of the species. You can come in and watch if you want, sweetie. We have a little visitor. He's going to tell me how I'm doing. Almost done. So it's almost analogous to quenching of the polymer or fluorescence quenching, where the polymer is just quenching itself and electrons can't get into the external circuit because we have this internal electron transfer. And you can actually see that with spectroelectric chemistry, where the polythiophene is losing that bipolar on peak after some time of charging. We've then gone on to look at the doping mechanism with EQCMD and also with deconvolution of the cyclical tamograms. We've seen the mass transfer is not really affected for the conjugated The mass transfer is not really affected. Thank you, sweetie. Maybe stand over here. Okay, good. The mass transfer is not really affected with conjugated radical polymers. It still seems to be dominated by the anion. So we don't see any evidence of internal electron transfer affecting external mass transfer. So I'm going to wrap up. We spent a lot of time talking about the mechanisms of electron and ion transport in radical polymer batteries and cross-linking and solubility considerations. Less time on conjugated radical polymers. I can follow up with you on that later if you're interested. And then I wanted to emphasize some parting thoughts for you. I did not show you some battery that was going to save the world and be recyclable, but that's where my group wants to go. We want to focus on recyclable and metal-free chemistries, and I'm still very enthusiastic about this materials platform in that venue. We still need to consider the issues of dissolution and improving capacity. Electron and ion transport still really isn't understood, and I think that's a very fun place to dabble and investigate. And then future studies for any of you working in the area, I would highly encourage you to start quantifying your radical loading and quantifying the composition of your real polymer, because I think some of the things that we observe might be explained by these other groups that we're really not currently considering. And finally, as a parting thought, I am the deputy editor of ACS Applied Polymer Materials, and while I have a captive audience, I am confident that many of you have work that would be suitable for our journal. So as long as it's applied in nature, it could be a good venue for us, and we're part of the ACS Applied Materials and Interfaces family. Okay, so with that, I want to thank my group and the students who did it. A lot of this work was funded by DOE and now ACS PRF. So thank you very much, and I'm very excited to take your questions. Thank you. I'm not sure if I should stop sharing, so I'll leave it here.
Thank you, Jodie. That was a great talk. I give the word to James first, so let him give the first question.
Yeah, thanks, Jodie. That was really, really interesting. I've got lots and lots of questions that I want to ask, and maybe I'll let other people have a go, and I could always contact you later. The QCM study is really, really nice, super nice work, and it's really interesting to see how it's not that conventional way of thinking that you have to have the anions coming in, diffusing in. It's already there, and it's more of an expulsion in terms of the cation as well. The question I have is that you've got this triflate group, which is large, and you've got this lithium cation, which is small, and you can see that expulsion. So what happens when you go to, say, a larger cation? A lot of people work with these, so like a tetrabutyl ammonium. Do you see the same thing in terms of what's going on? So does the size of that cation actually affect that process as well?
I love your question. We're addressing that right now in a paper that we are submitting very soon. With a cation of that size, my view is that it's much harder to go in and out of the electrode. So what we are seeing now is that with the large, bulky cations, the anion is the one that's transferring. We didn't see those double peaks. We only see one peak from the anion. So I think it's just too massive to participate in that secondary mechanism. Okay.
If I can ask one more question before I let other people have a go. So with your study where you quantify the different species, you talk about the secondary amine and the nitroxide and the N-oxammonium cation. But the other one that's normally obvious for nitroxide is a hydroxylamine type species as well.
Right,
so do you see anything, any of that kind of interacting as well? Because that's obviously going to be an important species as well.
Right. You bring up a great point. I didn't mention that, and I should. With us, when in our analysis, we do not see evidence of that species, unless we're overlooking it. But I know that species can result by certain synthesis and treatments. But absolutely, yes, you should consider that species. I would add that onto the list.
Great.
Yeah.
I might have
yeah, you go, Jan.
maybe a naive question. Maybe that's not even a relevant thing. So James asked about the type of cation used in the electrolytes. Do the anions have a large effect on what happens with the batteries at all? Because usually we use either triflates or chloride.
They really do. So my first answer to that question is in the Nature Materials paper, we also look at the perchlorate and BF4. And BF4, oh man, that's a weird one. It is very different. And honestly, we didn't really explain it very well in the paper because we didn't pin it down. And we're now doing a follow-up study on a whole series related to James's question. But I think the governing factors are going to be anion mobility in the liquid electrolyte, and then the solvation shell in the liquid electrolyte, and then finally, for that salt or electrolyte cation-anion couple, are they solvent separated or contact ion pair? How much energy does it take to break that pair in the external electrolyte to then get the anion into the electrode? So I think there's a lot of factors there that haven't been untangled.
Do you have any other questions, James, yourself, or can I start reading the questions?
You start reading some questions.
So first question was from Professor Andrew Whitaker. He's from University of Queensland, and he comments you on a great talk. He does say your son is very cute. And his actual answer is, can you please comment a little more fully on prospects of achieving commercially relevant stability?
Yeah, well, thank you, Andrew. And I'm just glad that my son was wearing a shirt. So now for commercial stability, to be honest with you, I'm not a very entrepreneurial person. You can see that I really love these mechanistic details. I've seen a lot of industrial interest in Japan through Hiro Nishida's and Kenichio Yasu's group. They've had a very long relationship with industry. NEC is one example. So I think industrialization is, I think commercialization is there. And there's probably a lot more tips and tricks going on there that are confidential that we don't know about. I think if we want it widespread, commercially prevalent, we have to start thinking about how can we perform just as well as lithium-ion batteries. And that's really hard to do because you have a whole battery community trying to replace lithium cobalt oxide, but they're replacing it with materials that still are energy dense, presents a safety issue. Recycling is not, you know, they're trying to solve that problem with more problems to come. But I think we have to get the capacity higher to solve this problem. And there's a few materials that look really promising, but they have their own issues, usually with the cyclability and the stability. So I think that's where, if you were going to design the next research project, I think that's where you should be thinking about.
We have a similar question from Marco Enriquez, who is asking that the current batteries have a lot of heat forming either when charging or discharging, and whether this can be overcome with the organic electrodes. And secondly, what do you think the next generation of organic electrodes should have in order to have better capacity while retaining long-term stability?
Yeah.
How to make the best of all?
Yeah, I want to make a joke, but about wishing, but we'll leave that. I think the first question was dealing with thermal management issues. I haven't seen a lot of work on that. But I also haven't done a literature search for it, but I think that's a really interesting question, because when you start to get up to these batteries that are fast charging, thermal management becomes a major issue and safety consideration. So will organic batteries address that? I'm really not sure. And I think that's a neat area to think about. If I could design the perfect radical polymer, it would have a higher capacity. It would be it would also have a high segmental mobility, connecting to the first part of that talk with electron transport, and it would not dissolve. It's hard to get all of that in one platform, but I think it's fun. It's fun to work on little pieces of it. I think we'll get there.
The next question is from Nathan Boaz, also an expert in the field. So thank you, Jodie. Great talk, first of all. I have also made Ptma and found limited oxidation. Do you think that your solubility parameters for each species might be affecting this, as the polymers are further oxidized, causing some kind of aggregation?
Yeah, I think there's a, if I understand the question correctly, when we were doing our solubility parameter studies, we were considering the true state of the polymer with those three groups. So when we were calculating the group contributions that are reported in the paper, those were back calculated considering the true composition of the polymer. So we did our best to capture those little details. In a battery environment, as the polymer goes through its states of charge, its solubility will most certainly change. And for Ptma, my opinion is that it is most soluble in its nitroxide radical form based on what we're seeing. So if you want to think about solubility, worst case scenario, you could go to a nitroxide radical polymer that is has a lower content of the oxoammonium cation, because it seems like the oxoammonium cation form is not soluble in anything, not even water, which I thought was kind of interesting.
Right, I think, somebody raised their hand, sorry, I just need to find whom. Zongfen, okay, allowed to talk. Zongfen, can you?
Yes, can you hear me?
Yes, we can.
Hi.
Hey, Judy, how are you?
Good, I hope you are well.
That's great. I really enjoy your talk, Judy. It's just fantastic. I got two questions, if I could. The first one is related to your CV through your EQCMD method. From your CV, you see that there's two peaks.
Yeah.
While you're cycling, it's in slide 27, I think. So my question is, we often not see this one when we do in a real coin cell, real battery system. But
right.
According to your finding, that two type of the ion diffusion must be also exist in the real battery system. And what do you reckon the difference? Why you can see this one in EQCMD, but we can't see this in a real coin cell CV?
Yeah, sure. I think I'm going to do some guessing here. So first, with the EQCMD, this is a pure polymer film. We cannot have carbon additive in the sample because it will invalidate the measurement due to the dimensions and everything.
Sure.
And we need the film to be totally smooth. So this is a representation of what the pure polymer film is doing.
Yeah.
Does this translate to the battery platform where you have a lot of carbon additive? I can't say. I'm not sure, because with the carbon additive, you now have interactions between the polymer and the carbon. And I think it's much more complicated than that. So if you don't see it in the battery platform, you know, I wouldn't worry. It doesn't mean you did it wrong or anything. It's just a different environment. It may not be happening. And then the other question is, does this little feature affect performance? I'm not really sure. I mean, it's a slightly lower potential. Is that something I want to get rid of? I'm not sure, but it's a curiosity. Yeah, I hope that answers your question.
Would this affected by the kinetics of the ions diffusion? Because if your ion diffusion is not match up with your electron transfer, then you definitely will get something like more polarization, which you can see from the lithium one, which go to lower potential when you reduce it back, right?
Right. I think that's a possibility. And then we also need to consider that the electrode, even your electrode will have some electrolyte penetration in it, even with carbon in it. But there's still some reservoir of salt in the electrode. Yeah. So that may get consumed, and then that may allow anions from the bulk to come in. Just different ways of thinking about it.
Okay, so if I could, sorry, Yen, if I could, I can ask another question just related to your slide 46. When you do the work on finding a different solvent for the system, you can see you're finding a good solvent which you can maintain the electrode nicely, but the conventional one, you see something rip off after the cycling. But where do you pay attention to the polarization or the charge and discharge for the predicted one, the very left-hand side one, which the charge and discharge have a much larger polarization than the usual one or the common one, which might be not the good solvent as you predict. How do you comment on that? Yeah,
I think this was this was like a one-off experiment, so I can't say that we fully understand the differences right now, and I haven't dug into the. I don't have the voltage profiles up here for the CD, so it's hard for me to comment on that. Right? Yes, yeah, for the charge discharge. But yeah, the electrode held together a lot better, and we made no effort. I would like to say we made no effort to optimize the composition. We just picked this composition and put it in there. Sure. So it's possible that if we lowered the PMMA, we may get some different behavior. So I'm not saying that this is the optimum fraction of components. We just wanted to compare them head to head. Obviously, you would want a lot more PTMA in there and a lot less Super P and PMMA. So we can consider that. And also the capacity in the cell is not very high. And that's probably what caught your eye, because when we make cells with some other optimized compositions, we can get almost a theoretical. Yeah. Yeah, so this was just a head-to-head comparison for demonstration.
Okay, great. Thanks, Julie.
Thank you.
James, do you have any final question yourself by any chance?
I've got a few things, but I might take them offline as well. It might be easier just to put them in an email and we can talk offline about them. They're probably a little bit more specialized than for this general audience.
Wonderful. Yeah, that would be fantastic. We can talk another time. Yep. As convenient. Yeah. Yeah.
Yeah, I love it how many questions there were. So obviously we chose a really relevant topic to Queenslanders.
Great.
I have just one question to sort of wrap it up, and it's for all the PhD students we have, and I think it's at least half of the people we have in the audience are PhD students. What would be your message for PhD students? Sort of what does it take to make it in academia, in your opinion? And try to say the nice things.
It is so, I mean, that question is so funny because when my students heard that one time I was asked to be on a work-life balance panel, and one of my students heard that and just started laughing because my life is like totally, everything's, as you could even see during the presentation, everything's intermeshed, family and work and everything. And that's just how it is these days. So I think it's really important to have a life and to enjoy your life. but that doesn't mean you don't work hard. I work really hard, but at the same time, it's because I enjoy it. I especially love this topic. So find a topic you love, find a topic you can be obsessed with, and let it mingle into your life and enjoy it. So make sure you have fun, but not too much fun.
Thank you, Jodie. Well, I guess it's time to wrap up. So thank you again for taking your time to be with us. Thank you, James, for introducing Jodie and also for your recommendation. It was a great talk. And again, on behalf of the RACI Queensland Polymer Group, thank you for attending. And,
thank you. And I would like to also comment, I hope that some of you may follow up with me. I see this as an opportunity to share knowledge, and this was a one-way thing. So let me hear back from you another time. James too. Thank you.
Thank you.
Okay.
Thanks, John.
Good night.
Yeah. Have a nice day. Good night.